we'll move on to our next speaker, Paul Agnew, speaking on geochemistry. Paul is an exploration geologist with more than 29 years' experience with Rio Tinto exploration, searching for a wide range of commodities in diverse environments. As chief geochemist for RTX, he spent more than a decade providing geochemical technical support to global exploration programs and building technical capability throughout the organization. In 2010, he took the role of chief geologist, technical support and technology development, leading a team of technical specialists, providing global support and managing internal and external R&D activities, focused on the delivery of innovative exploration technologies to improve the efficiency and effectiveness of mineral exploration. Thanks, Paul.
Well, good morning, everybody. I've been asked by the organising committee to give you a 30,000-foot view of the state of the art of exploration geochemistry over the past decade. So let's start at 50,000 feet and have a look at the performance of the exploration industry as a whole over the past decade. This chart from Richard Schoddy shows very, very well the number of discoveries over time versus exploration expenditure. And it's very clear that this decade has indeed been a remarkable decade. We started out with the highest number of discoveries ever recorded in history of this chart. And as exploration expenditure grew to what may be described as absurd levels, the rate of discoveries plummeted to the point where at the end of the decade, we find ourselves with the lowest rate of discovery ever recorded, even taking into account an estimate of unreported discoveries which may still be to come. What's going on here? Is this a sign of decreasing effectiveness of many of our exploration techniques and technologies as we move into ever more challenging exploration terrains? Does geochemistry have a role to play in this decline? If I had to form a view of the state of the art of exploration geochemistry in 2017, I'd have to say, people, all is not well. This decade has seen a slow but steady shift in exploration focus towards deeper targets and towards areas of post-mineral cover. The enthusiasm to explore some of the more exotic places in the world has been somewhat tempered as the realities of sovereign risk hit home hard when you try to convert that discovery into a mine. This has led to a bit of a retreat into the more mature exploration terrains, which of course from a geochemical perspective have generally been quite heavily sampled. The effectiveness of conventional geochemical exploration is diminishing in this new exploration paradigm. The picture on the right here shows very well what I'm talking about. This photo is taken 500 metres above the very deep ore body at Oyu Tolgoi in Mongolia, the Heruga copper system. Those soils and rocks have absolutely no geochemical response whatsoever. In fact, the only indication that there's anything around here is a bit of epidote at surface. And I'll be saying a little bit more about that later on in the talk. In Australia, the realities of declining discovery rates are hitting home hard. And for the first time ever, the entire Australian geoscience community is taking action to address the impacts of post-mineral cover on discovery. The Exploration Technologies Cooperative Research Centre is developing new drilling technologies and supporting technologies for a future of exploration drilling for deeper targets under post-mineral cover. And the Uncover Australia initiative, an initiative driven by the Australian Academy of Science, has seen the entire geoscience community, industry geologists, government geologists and researchers, come together for the first time in history and agree on a multi-decadal plan to develop the technology and collect the data and do the research that Australia needs to turn around that declining discovery rate in a future that's dominated by exploration under post-mineral cover. I doubt that this challenge is unique to Australia. We simply have to get better at exploring deeper and exploring through post-mineral cover. So this decade presents us with a bit of a challenge, particularly for the geochemists. We need effective geochemical techniques and technologies that support successful exploration for deep targets and for exploration under post-mineral cover. I think the past decade has been a period of adjustment between an old reality where exploration in residual terrains and geochemical methods are very, very effective in these terrains, to a new exploration paradigm where our targets are deeper and post-mineral cover really does challenge the effectiveness of conventional geochemical methods. Of course, there's always opportunities for conventional geochemical methods to turn up discoveries. And the diagram, the image on the right shows very well what's really one of the great discoveries of the decade from Ivanhoe. All it took was a little bit of lateral thinking from Ivanhoe, some regional stream sediment surveys, and some good old-fashioned soil surveys, and it lit that ore body up like nothing ever before. But of course, these discoveries are often to be had in areas of considerable sovereign risk, and indeed considerable personal risk in some instances for the exploration geologists doing the work. Let's now have a look at some of the decadal trends in geochemistry over the past 10 years. First observation I would make is we are seeing virtually the extinction of large regional geochemical surveys. When I started out as a young baby geologist working in Papua New Guinea, we used to fly around in helicopters and collect hundreds of stream sediment samples and follow-up soil samples covering huge areas. Those surveys, and the surveys of our competitors at that time, pretty much found all of the mineralisation that's now known in Papua New Guinea. Ever since the 60s, with the advent of inexpensive multi-element geochemistry, organisations all over the world have collected large numbers of geochemical samples on prospects and regional scales. Add to that, in the 80s and 90s, large, low-density regional, continental mapping programs, such as you can see on the right-hand side here, pioneered by the Geological Survey of US with the New Ray Stream sediment sample, just showing the remarkable coverage and the remarkable geochemical mapping capability of these enormous surveys. But there's no doubt about it, new geochemical data acquisition is diminishing fast. Most of the mineral belts have already been heavily sampled, and importantly, open range access for this sort of low impact regional sampling is increasingly difficult in many jurisdictions. Fortunately, there's been some offset against this. This decade has seen unprecedented access to free geochemical data. Never before have we had such huge volumes of legacy geochemical data so readily available to us via the internet. The image on the right there shows Rio Tinto Exploration's global public domain geochemical database. It now has in excess of 16 million records in it, and it grows every day. This gives us an unprecedented capacity to review geochemical data on any scale and to look for regional trends and anomalies that may not have been apparent in the past, or importantly, may not have been relevant in the past, but are today. Most important, this data gives us an opportunity to understand where the gaps exist in sampling and where the gaps exist in data quality. It may have been sampled, but is the data of sufficient quality to find the ore body? Analytical advances continue to drive geochemical exploration capability. Ultra-low detection levels for crustal have reached levels lower than crustal abundance for pathfinder elements such as moly and tungsten, selenium, tellurium, bismuth, antimony, arsenic, lithium and thallium. In my years as a geochemist, these elements were generally many of these elements were generally fairly useless. They were either not analysed, or if they were analysed, they were almost always below detection or unreliably at or near detection levels. If you look at the image on the right-hand side, there's some ridge and spur soil samples collected over a porphyry system. You can see in the top image there is a bit of a copper anomaly there. It's not particularly compelling, a little bit spotty and certainly pretty low level. But that copper anomaly we can now see is supported by a very, very coherent and consistent tellurium anomaly. And indeed, on drilling that copper anomaly, there is a deep porphyry system under there, and it is highlighted by a tellurium anomaly at surface of just less than 1 part per million in many cases. So these new detection limits are very important tools for the detection of mineral systems that remain deep and uneroded, and also for the detection of primary dispersion halos on the edge of post-mineral cover. For more than half a century, geologists and geochemists have been looking for field-portable analytical capability. And this is one of the very first field-portable laboratories that ever existed. It's the Craystar. It was a ship with a helicopter on it and a laboratory down in the hull, and every morning the geologists would go out floating around the islands of Papua New Guinea, collect stream sediment samples, come back in the evening, and overnight those samples would be analysed with the basic AAS equipment down in the hull of the ship. The very next morning, any anomalous results would be followed up. Well, this decade has seen some pretty dramatic changes in portable laboratories. They're a hell of a lot smaller, they're a hell of a lot cheaper. The Reflex Labiter rig, developed by the CRC for Deep Exploration Technologies, offers XRF geochemistry, spectral mineralogy, and XRD mineral identification on cuttings at the drill rig in a small trailer-mounted laboratory. The Mineralised system is offering high-resolution XRF geochemical analysis of drill core on as high a resolution as 1 analysis per centimetre down the core, and that system sits on that desk. So things are getting smaller and things are getting far, far, far better in terms of analytical capability. But it's really the handheld devices which have matured in this decade. This decade has kind of seen that dream of portable analytical equipment come to fruition. We've seen expanded analytical suites and far better detection limits on the handheld XRF equipment, better data management, and importantly, better quality control. We're even starting to see emerging light trace element capability with the LIBS handheld analyzer. I guess for me, the learning has been that there really is no substitute for a well-prepared representative sample. Portable data is no substitute for laboratory data unless you can present to that piece of equipment a homogeneous sample. And that really does highlight one of the key limitations of this fantastic equipment. Nevertheless, it is ideal for real-time decision making. I've seen it in use widely across the industry and it does a great job. And it's also really good for assisting in that mineral identification for those problematic minerals that you're struggling with out in the field, which is certainly what I find myself using it for more and more. I think one of the most significant advances in geochemistry over the decade has been the proliferation of portable spectral devices to collect spectral mineralogy. Add to that the ACIRIS processing algorithms, which consistently extract far more information from those spectra than we're used to having, and integrate that spectral mineralogy with geochemistry, and the geochemists of this decade have really an unprecedented capacity to model and predict alteration, lithologies, and pathfinder element associations. I just want to acknowledge the work of geochemical consultant Scott Halley here. Scott has really pioneered a whole new approach to interpreting geochemistry, which puts that geochemistry very firmly in the context of mineralogy and lithology. And he's developed a whole series of fantastic plots in IAGAS software, and if you can integrate that with measured spectral mineralogy, you really are in a very powerful space, and you're fully utilising those 30 or 40 elements we traditionally analyse for. But without a doubt, in my opinion, the most exciting development this decade, and again, I put it under the auspice of geochemistry, is hyperspectral core scanning. This has given us unprecedented visualisation capacity for alteration. You can see on the core scan image on the right-hand side of the screen there, we've got chlorite in green, which appears to have been overprinted by biotite in brown, which is in turn cross-cut by silicification and quartz veins, which have white mica selvages, which have in turn been cross-cut by gypsum veins in pink. No geologist can map with that level of accuracy and detail and consistency. And the advantage of these systems, and this is why I include it as a kind of a geochemistry development, is they provide us with semi-quantified mineralogy information. So you can see on the diagram on the left there, This is semi-quantified abundance of various minerals down a drill hole. So for the first time ever, geochemists can add another 30 or 40 mineral variables to the 30 or 40 elemental variables that they have to interpret. So things are getting pretty complicated. We've got a lot of data to deal with, but if you have the right interpretation and visualization techniques, this really provides us with remarkable capacity to both domain drill holes accurately and consistently, and ultimately to domain entire ore bodies in terms of their mineral types and their processing and marketing and product capabilities. Geochemical dispersion through post-mineral cover. I mentioned earlier how we need to get better at exploring in areas of post-mineral cover. Well, detecting that geochemical dispersion through that cover has been something of a holy grail for geochemists. That sort of dispersion is well documented, and it should be detectable with appropriate surface sampling and digestion and analysis. I'd have to say, however, after widespread adoption in the 90s and early 2000s by industry, by academia, and indeed by commercial laboratories, there were remarkably few discoveries. The image on the right shows a multivariate image of the kind of elemental suite that is exactly what would be expected to be dispersing through post-mineral cover. You can see in the histogram there that there's a lovely anomalous population there, and the patterns of those anomalous samples are interesting looking donut and circular-like features. Surely this is exactly the kind of response that the orientation surveys told us would be related with mineralisation. Well, unfortunately, in that instance, none of those anomalies were, and across the whole industry, we didn't see that spike in discovery rate which would have happened if we were consistently predicting mineralisation through post-mineral cover. I guess the penny really dropped for me in 2009 when a final report from CSIRO under an AMIRA project, predictive geochemistry in areas of transported overburden, really highlighted just how complex these signals are, how they are transient in time, and how they are very, very regolith and climate specific. So I'd have to say, for the holy grail of geochemistry, detection of dispersion through post-mineral cover, we ain't there yet. We've got a long way to go, and I'm starting to wonder if we're ever going to get there. Final observation for decadal trends in geochemistry is I think our exploration geochemists are an ageing demographic. I don't know, but all of the geochemists I know have grey hair, or no hair in some cases, including myself. There are a few young'uns out there, but my feeling is we have a lot more experienced geochemists retiring than we have young geochemists graduating. I did a search in LinkedIn for jobs with the title geochemist. There are 1,200 geochemists, assuming we're all on LinkedIn, servicing the entire global exploration industry. Compare that to 80,000 geologists. And I ask you, is 1 in 80 the right ratio to see us into the next decade to ensure that geochemistry continues to contribute discovery? I'm not sure it is. So the academia, you need to keep encouraging and teaching undergraduates to study geochemistry. And the industry geochemists that are out there, pass it on while you can. It's important for our future. And what does that future look like? Well, despite many significant technology developments of the past decade, geochemistry, probably along with other search technologies, has not been able to arrest that globally declining discovery rate. Opportunities for traditional geochemical methods for the detection of near-surface mineralisation are absolutely still there, but they're often accompanied by greater sovereign risk and in the remaining parts of the Earth that are underexplored, and indeed by greater personal risks for the geologist undertaking that exploration. Will the next decade be make or break for geochemistry? Will geochemistry continue to be the only deep targeting tool the exploration industry has? What can we do? I think the geochemists need to shift focus to some new geochemical technologies for detecting deep and uneroded mineralisation and mineralised systems beneath concealed cover. What do I mean by that? We need the capacity to detect distal halos, both on the edge of cover and from deep uneroded mineralisation. We need to know about the fertility of a system before it's been discovered. It has a remarkable effect on your tolerance for risk and your persistence. If you know there's a good ore body around there somewhere, you just need to find it. And finally, we need robust geochemical vectoring. Is it really possible for geochemical methodology to give you the X, Y, Z of that next drill hole? I want to end up briefly talking about a couple of technologies which I believe are going to carry us into this future. The first one is automated mineralogy. This is techniques basically using mineral liberation analyzers and QEMSEMs and automated electron microscopy. The image you can see there is a single grain, and it comes from the base of a conglomerate unit which covers a vast area of prospective rock. And if you look at the minerals as they're mapped on that grain, you can see in yellow there you've got copper bornite associated with the purple chalcocite, and that is intergrown with muscovite and quartz and biotite. So the porphyry geologists out there will know that single grain must have been derived from porphyry-style mineralisation. Almost no doubt about it. This is a very sophisticated way of knowing that that conglomerate colluvial fan must have eroded mineralisation concealed under there somewhere. But we can go a step further. Here's another image showing all of the sulfide minerals recovered from a stream sediment sample. Lots of pyrite in there. The beauty of automated mineralogy is that mineralogy is accurately quantified. So for the first time ever, geochemists can produce a normal probability plot of pyrite content in a geochemical sample. And you can look for those anomalous populations in exactly the same way we do with other elements. The second technology which I believe is going to carry geochemistry into the future is mineral chemistry. Ever since geochemistry was invented, we've been taking one rock or one soil and doing a bulk or sometimes a partial geochemical analysis of that sample. But of course that sample is made up of lots of individual minerals. And the diamond guys worked this out a long time ago. If we take one of those minerals and analyse its chemistry, then that chemistry is far more constrained in terms of the stoichiometry, the elements that can and cannot fit into that crystal lattice in various proportions, and also the crystallisation conditions in terms of temperature, pressure, and fluid compositions. So that level of knowledge is absolutely far more powerful than anything you can derive from a bulk analysis of a rock or sediment. Let me talk to you now a little bit about some really cool research which is showing very, very well how you can use mineral chemistry. We all know the alteration systems around porphyry coppers. The propylitic alteration is by far the biggest. If we erode that system, put it into the landscape, you can see it's quite a substantial target, and then pop that under cover, you see that because of the size of that alteration system, we have the potential here to detect it on the edge of cover, maybe from distances of 1 to 6 kilometres away. So some award-winning research down at Codes is looking at identifying epidote from this fertile propylitic alteration. Epidote's a fairly common mineral, but the Codes research has demonstrated that we can use the chemistry of epidote to associate it with a fertile porphyry system. In RTX, we've developed sophisticated data analytics supported classification tools which allow us to take these samples collected along the edge of cover and hopefully identify those few samples which appear to be associated with a fertile porphyry system. Zinc and manganese in chloride also appear to be a robust predictor of porphyry fertility. Codes research has demonstrated that chlorite fertility is associated with almost all of the very large copper deposits that they've studied. And indicators of system fertility are important if you're going to justify drilling through post-mineral cover. And finally, research by Jamie Wilkinson, one of the Codes research partners at the Natural History Museum, has shown that chlorite mineral chemistry can actually be used to predict the centre of a distance to a porphyry system. Codes research has demonstrated that compositional gradients in chlorite can indicate proximity to systems from up to 3.5 kilometres away. It's not easy, but if you've got the right data, if you've got the right calibration formula, those distances can be converted into three-dimensional spheres, and where those spheres intersect, it just may tell you where that porphyry copper system sits undercover. So look out, geophysicists, because for the first time ever, looks like the geochemists are going to be able to give you an XYZ for the next drill target. So, summing up, I've got 30 seconds. Key messages. It's been a decade of transition from geochemical techniques that are highly effective in residual terrains for the discovery of near-surface mineralisation to terrains where post-mineral cover and deep uneroded targets really do challenge the effectiveness of geochemistry. This decade has delivered some of the tools and technologies supporting discovery in increasingly difficult environments. But we need to continue to develop and build new skill sets and mindsets for the next decade. I'm optimistic about the future. We have ultra-low detection limits, vast quantities of legacy geochemistry, spectral mineralogy to integrate with our geochemistry, and microanalytical equipment for high-volume mineralogy and mineral chemistry. With exploratory data analysis and advanced data analytics, I think we're in a great space into the future, and there's some exciting tools developing for distal halo detection, fertility prediction, and robust vectoring. Thanks very much for your attention, and thanks to the sponsors and researchers. Thank you.
Thank you very much. That was very good. Thank you.
I'm sorry about the time.
No, it's perfect, yeah. We still have a couple minutes. So we have a few minutes for questions before dispersing for the coffee break. If there are any questions, if you could come to the microphone, ideally, if you feel you can shout it out and we can hear, we can repeat the question back.
The question was, where do I see hydrogeochemistry in the future? And thanks, Cam. I am remiss in not mentioning hydrogeochemistry because it has absolutely not been a feature of this decade for many exploration companies, and that includes my own. And I think it plays an important role. There's absolutely one sample media which can carry dispersion through post-mineral cover, and that's water. I believe it's grossly underutilised. People are a bit intimidated and scared of hydrogeochemistry. I don't think that's entirely justified. It's a new skill set, it's a new mindset, and we need to do a lot more of it. I think anyone drilling a hole without sampling the water in that hole is crazy.
All right. We would still have time for another question if there is one from the audience. Way at the back there.
Yeah, the question was, I haven't said anything about isotope geochemistry. That's because I don't know anything about isotope geochemistry. It's always a mistake to get up in front of lots of people and talk about stuff you don't know anything about. Look, it's an exciting field. There is some great work being done in isotope geochemistry, particularly at Queen's, and with people such as Kurt Kaiser over the years. It's tough analytically. But it has great potential, and I am a fan. I'm just not a deeply knowledgeable person, so I haven't mentioned it.
Okay. All right, with that, we'll break for coffee. Please be back in the room for 10:45 sharp. That's when the next speaker will start. Thanks, see you soon.